Okay, right, we'll summarise this on here. Graphs. I don't know, graphs of what? You've got these options. You can graph the concentration against time. Right, so concentration, I'll just put concon, shorthand for concentration. Graph against time, I'll put versus, same sort of thing. Or you can do rate against time. No, do rate against concentration. But what you're recording for the rate here is 1 over time. All right, now what this means is that you have to find a point where you think your reaction has, well, not finished. One of the important things with this is that we are most interested in what we would call the initial rate. And the initial rate, you can't measure necessarily, you know, just at the absolute fraction of a second that the reaction actually starts. So you have to do an estimate. 1 over time is an estimate of rate. But you usually have to select a point in the reaction where you've got a recognizable outcome. The reaction that you're going to be using, I'm going to explain towards the end of this afternoon because you're going to be using it tomorrow afternoon. And it's a reaction between sodium thiosulfate and hydrochloric acid that produces a pale yellow precipitate of sulfur. A precipitate is just solid particles forming in a liquid. Now, what you can do with that is use the, the degree of opaqueness or opacity of the solution to actually judge when you've reached a point that you can identify. And so we have if we put a dot or a cross on a piece of paper under or behind the reaction, then when that disappears, you've got a certain amount of sulfur. And then if you change the concentration, or you can do it with temperature, and you do it again, you judge when that cross or spot disappears. It's amazingly consistent, and you get really good results. So we count that as the initial rate. You could leave it, and it will go on, and if you leave the reaction running, you'll find that it produces more and more sulfur anyway, but we just use that as our estimate. So this idea of 1 over time is 1 over the time it takes to reach an identifiable point in the reaction, in this case. So you've got these different sorts of graph then. Concentration against time, concentration on the y, time on the x. Rate against concentration, rate on the y, concentration on the x. And for a first order reaction then, you get these very distinctive curves and, well, lines. So first order. For that one, the concentration against time, then you've got this very, very clear rounded curve. All right, so that's probably be easier if I don't know, call that one, call it 1 and 2, if you like, and that's a graph 1. But the graph 2, what is rather lovely about that is it produces a straight line, yeah. Or as near as, you know, I mean, it's very, very hard to produce perfect straight lines, particularly from, experimental results. But plotting the rate in terms of 1 against time on the vertical axis and concentration on the horizontal, you get a straight line if it's a first order reaction. And what that's telling us is when we double the concentration of our, well, whichever reactant we're interested in, the rate doubles as well. If we treble it, the rate trebles. If we quadruple it, the rate quadruples. They go up by the same amount to the power of 1. So a rather nice straight line. Now the other graph on this sheet, the one on the right hand side for the first order reactions, is showing you how you can use the tangents. And we've done tangent drawing, haven't we? It is a tricky thing to get exactly right. But if you are trying to find a rate at a specific concentration, which is marked on that graph with a little asterisk, then you draw a tangent, and he's done it the easy way on here by just getting it to cross the axes, because it's so much easier to read off the values like that. The tangent is the gradient at that point. So y divided by x, the change in the vertical value by the change in the horizontal value. And you get your rate at that point. Okay. Now, you know, you plotted that graph from that information anyway, so we've got a fairly straightforward sort of result there. Now, if we move on, it gets a little more complicated. So if we look at the second order reaction, which is the situation where if you double the concentration, the rate goes up by a factor of 4, 2 to the power of 2, and it's that power which is the order of reaction. If you were to treble the concentration, the rate would go up by what? The power, remember, is the index. It's the the order is the power. So if this is one we didn't have. We used 2 and 4. But for an example, if you do the concentration times 3, then the rate will go up by what? 9. Yeah, 3 to the power 2. And it's that 2 there which is the order. Yeah? And so, you know, you have to take example values to work this out, and that's what the worksheet was last week. Now, we've got slightly different looking graphs here. The first one, concentration against time. This time, it gives us a slightly steeper curve. That's the important thing. But of course, if you're just drawing one curve, you're not going to see that, you know, because you haven't got another one to compare it with. So that in itself can actually be, you know, not very useful. But if we do an equivalent, you know, graph 1 for this against the one up there, that's a rounded curve up there. This one is a sort of flatter one. And I'm not sure I've managed to flatten it out enough there. Yeah, it's dropped quicker. All right, because the effect is increased, if you like, by the fact that we're squaring it rather than just having it to the power 1. And then significantly, if we draw the second graph that we've got here, rate versus concentration, rate just being 1 over time, this time, rather than getting a straight line, you get a curve. All right, now this is a fairly wide curve that you get for that. But on here you can see there is a third type of graph. And this time it's rate against concentration squared. Aha! That figures, doesn't it? That if you do rate against concentration squared, when, whoops, what we're looking at, of course, is the, you know, the need to square the change in the concentration. Well, what do you know? We get a straight line. Okay. So yeah, I'm not going to draw that one. It's on your sheet. All right. So there can potentially be a lot of graph drawing in this. If you then look down at the bottom, you've got, as I say, 2 lines on each of these axes. We've got the 0 order reaction. And for a 0 order reaction, if you double the concentration, the rate is affected in what way? Stays the same, yes, because 2 to the power 0 is 1. Okay. However, if you reduce the concentration, you'll find, you know, you've got your first graph there, just gives you a straight line down there for your 0 order. But if you then look at the rate against concentration, you get a horizontal line. Now, the one that you're going to do for the coursework, which I think is next week, you do that practical, or you start doing it. I've put 3 sessions aside for you to get everything done in and repeat anything that needs doing. You have to be quite creative to get a horizontal line for one of them. All right. Yeah, that's giving too much away, isn't it? But that, yeah, that horizontal one for the 0 order there. All right. So 0 order, for the first graph, then you just get a diagonal going down like that. But for your second one, that's the one that's quite critical. All right, because you're going to measure time. You then do 1 over time, and the risk is that you try and plot it too accurately, and that then often doesn't give you a straight line. If you round things up or down quite a lot, you'll find that you get a much straighter line. You can also see, if you know, look at that last set of axes there, that you've got third order on there. So I'm not going in sensible sequence here, but the third order one. So here, let's just check that we're okay with this. If we do concentration times, let's say 2, it will be rate will multiply by 8, yeah. So 2 to the power 3, all right? In other words, 2 times 2 times 2, which is 8. And it's that which is our order of reaction. All right, and the graphs that we get for this, you have to compare them with the previous ones to actually get what's happening. So graph number 1 for this, where you've got concentration against time, you have a really steep sort of drop on it, you know, in comparison with the previous one. And this time for graph number 2, if you do rate against concentration, you get, whoops, yeah, that should be steeper than the previous one. Whoop, that one, yeah, it is. And this time you'll get a straight line if you do rate against concentration to the power 3. All right, so hopefully you can see the pattern. You know, theoretically, I suppose we could go up to any sort of order we wanted to. So, you know, if you had a, I don't know, a 6th order reaction, I don't think they exist, but you'd get a straight line if you plotted rate against concentration to the power 6. You know, that's what it's saying. But it requires you to sort of think about the algebra of this. But it's algebra that involves indices, which is always a little bit tricky. What we haven't got on here is the idea of using logarithms. But I think I won't go down that path. My maths isn't really quite as secure as it might be on that to do it reliably in this situation. But we will meet it, and we'll talk about logarithms. And I think, yeah, we've got that coming up over the page anyway. Now, down at the bottom of that big sheet, you've got measuring the rate of reaction, and we've considered some of these already. Loss of material, such as a gas, so you can either collect it in a syringe or do it on a balance, or you did it, and actually one of the best sets of results we got was the water bath with the upturned cylinders in, wasn't it? Those produce really nice curves. You know, if you've kept all the results and the graphs from all these, hopefully you will see where they're fitting into this now. Change in conductivity, we haven't done that, we're not going to. Change in pH, we haven't done and we're not going to. Changes in volumes of liquids as measured by a dilatometer, no idea how that works. And change in colour as measured by spectrophotometer, or quite simply a colorimeter, which I really must get that out and have a go with it. Now, things get a bit more complicated over the page. So apart from we've got the rate constant up there and saying its value changes with temperature, we're not considering temperature at the moment, all right? So you can see what's happening over the page. It gets very messy. Now, I don't like that particular equation, the way it's written there, but you can see where the logarithms are coming in here. But that equation, and I'm not doing this now, I'm coming back to it tomorrow, it's called the Arrhenius equation. And it's a little bit misleading on here, because I think this sheet was produced before we had things like equation editor on the computers. It's that old, all right? But what it is showing is that that's the Arrhenius constant. I think that's actually a subscript rather than... Oh, no, it's not, sorry. No, that is E. Have you met E? Yeah? What's the value of E? 2 point something, 18 something or other. Yeah. Do you know where it comes from? What E is? It's one of those constants like pi. And we just... I'm not sure how you describe it mathematically, but I believe E is... And it's one of those that goes on forever, if that's what an irrational number is, that just, yeah, it's one that you can't actually total up, yeah? I think it is 1 plus 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And, you know, obviously then, you know, where do you stop? Well, you don't, do you? That's why, you know, the number can have varying different values. And mathematically, it's a very important number. Yeah. I think that's what it is. So I may be wrong, but we meet E in various guises, and now I've sort of messed up the space I need. The rest of that equation is supposed to be the power of E. All right, so it's not up as far as it should be. It's E to the power of minus EA, which is the activation energy I mentioned to you yesterday with the enzymes, over RT. All right, so it should look like that. All right, and we will do it tomorrow properly, or we'll mess around with it properly tomorrow. You can see A is the Arrhenius constant. The gas constant we have actually met before. I can't think where that was, but we have definitely used it for something. Temperature in kelvins. And then EA is the activation energy, all right, in joules, not kilojoules. And you will be able to work out from your practical work the activation energy for your reaction using a version of that, all right? But that's coming up tomorrow and further beyond. So we'll, yeah, hang on to those because we'll be coming back to the other side of it. I think what I need to do is to get used to thinking about working stuff out, and I'm going to use some A-level example questions on rates actually for this, because I know this moves quite quickly and it gets very complex and it does require good maths, which, you know, it is supposed to match up with roughly what you're doing at the moment. And I'm going to give you these 1, 4, yeah, which have got some answers attached to them. Let's stick this on pause. The first question then, a chemical reaction's first order with respect to compound X and second order with respect to compound Y. So it's write the rate equation for this reaction. So what's the first thing you write? Rate equals, yeah, don't forget that bit. So the rate equals, and after that it's then a little k, yes, followed by, yep, x in square brackets means concentration of x to the power, okay, sorry, let me read it again, 1, so we just leave that, and then y in square brackets to the power, no, you don't bother putting the 1 in. You don't, no. In the process of working it out, you might do if it was in an exam, but you, yeah, you don't put it in there. And I don't know whether, because we have got the mark scheme at the back, actually is a exam board mark scheme, I think, but it doesn't give us any indication of what is or isn't required there. So it's perhaps the smaller version of. All right, so because it's first order with respect to X, we could put a 1 in there, but we don't need it. Second order with respect to Y, that's where the 2 comes from. So the overall order of this reaction is, okay, so it's 1 plus 2 equals 3. And yeah, it's not often I get to write something like that on the board. But it just, you know, it shows where that information comes from. I mean, if this was an A-level exam, you know, if you were going to do A-level chemistry, you wouldn't have to put 1 plus 2 equals 3. But you know me and how I mark things, I'm looking for you demonstrating understanding, so I would want that in there. Now, I'm not doing this because you've got to answer any questions like this in the rates section, What I'm actually doing is trying to introduce the style of some A-level questions, because that's what you'll get when we're doing the equilibrium section. I will give you a set of questions like this on equilibrium to do as a sort of supervised assignment in class, open book exam if you like. We'll do some practical ones one week, and then you'll get them in class to do different ones to do in class the following week. And they are sort of this style, they're laid out like this. Okay, by what factor will the rate increase if the concentrations of X and Y are both doubled? I don't know if they give us any working out on that one to guide you. No, they don't. Okay. Oh, yes, it must change. Yeah. If you double X but leave Y alone, what will happen to the rate? It'll double. All right. So we already know it's times 2 if you double X. If you double Y, what happens to the rate if you leave X alone? Yeah, times 2 to the 2. And because they're multiplied together, you're sort of like that, aren't you? So it's going to multiply by 2 times 2 times 2, so it's times 8. I'm not going to ask you to do any like that. That's a slightly tricky one to do, because we've normally been just looking at what's the effect of one of them. But what you've got to think is, all right, if you do that one first, but then you do the other one on top of it, then you're going to get both the effects. Yeah, yeah. If you, you know, we've just looked at one at a time. But if you doubled one, you know, if you doubled X, so it'd double. Well, then if on top of that you double Y, well, it'll double to the power 2. So, you know, you're doubling to the power 2 what you've already doubled. Ooh, sorry about the English. All right, so this bit is what happens when you double the concentration of X. All right, that's the 2 to the power 1, if you like. That might make it easier if you put the 1 in there. And then because these are multiplied together, that's the Y bit of it. Because they're both happening, then, yeah, 2 times 2 times 2. Okay, the next bit on here is like the ones we had many hours of fun with last week. So, overall order of reaction between A and B. This is a different question. That always confuses me. Overall order of reaction. Explain how you reached your conclusion. Okay. Right, we haven't got one of them kept constant, have we? For A. Ooh, that's going to be awkward. Right, okay. Let's see what we can do with it then. Yeah, we can work out the order with respect to A, can't we? Because if that's kept constant, let's start with that, then when we double the concentration of A, what happens to this? It goes up by a factor of 4. Yeah? All right, so that is 2 to the power 2, all right? So if that's... All right, so the order with respect to A is 2. Okay. Now I've hit a tricky bit. It shows I'm not a chemist, doesn't it? All right. Okay. Ah, right. Okay. As if we do things to A, but we... Ah, it does. You're right. Yes. Oh, that's a sneaky one. No, that's all right. That's okay. Yeah. If we, I've just got to choose red for this so that it shows. Oh, right. Okay. No, we're being asked for, yeah, the overall. Oh, right. Okay. Determine the order with respect to compound B. All right. We've got, oh dear, no. I'm easily confused. No. It's the same. It's the same thing. If you double A, which we've done there, it goes up by 2 to the power 2. But if you double B, if you double A and you double B, yeah, then what happens here? It goes up by a factor of 4 again, doesn't it? All right, so that's times 2 to the 2. In other words, doubling B didn't have any effect because doubling A already does it by 2 to the 2. So changing B as well didn't make any difference. And that's a tricky question. So what's the overall rate order of reaction then? 2. Yeah, because the order with respect to A is, managed to work that one out, is 2. But the order with respect to B is going to be 0 because, you know, we can do things to B, but it doesn't change the effect that doing that to A had. So it would be 2 plus 0 is 2. I'm not going to try and put an explanation in there because you've got it on here. Right. It's weird though, order of reaction with respect to compound B. So I think I've missed something out. I think we should be able to determine that without having to think about B. So we know that that's 0. Because if we double A with the constant B, oh, that's interesting. That also leads to the rate times 4. Yeah, I've sort of done it backwards. You get the general idea, I hope, that if we double A, we can double it either from there to there or from there to there. But of course, you know, when you look down here, doubling A but keeping B constant had that effect. Didn't need to do that necessarily at the beginning. But doubling A and doubling B has the same effect. So B is not actually, the concentration of B is not having any effect on the rate of reaction. That's a strange sort of idea, isn't it, in your mind, that, you know, if you increase the concentration of a reactant, you'd think more particles, more collisions. Why doesn't the rate go up? I can't explain that one. I should be able to. Our overall rate then, our rate equation for the reaction then, rate equals, we should be able to do this all right. Okay. And then A to the power 2. Anything else? Nothing else. Because B to the power 0 is 1. So you don't need to put it in. All right. If you wanted to put the working in, I didn't need the times in there, but B to the 0, right, is K A to the 2 times 1 is just K A to the power 2. It's quite a useful one to have because you will need that for your assignment or something very similar. All right, you will hopefully lose one of the terms in your rate equation when you work that one out. Right, I clearly chose some quite complicated things here. But you can sometimes work backwards from answers, so, you know, don't assume you've got to know it all. You've done very little on this compared with what A-level students do. So what you have to do is to look for the bits that you think you understand and then sort of work backwards sometimes from an answer. And, you know, I mean, I don't teach enough of this to be as fluent in it as I perhaps should be, but... Right, calculate the value of the rate constant, stating its units. Okay, value of the rate constant. Well, if our rate, okay, is K times a to the power 2, then all we need to do is to choose any of those concentrations you like. It doesn't matter. I'm always tempted to take the one on the first row. So if you rearrange that, then K is rate divided by concentration of A to the power 2. Right, divide through by A squared. So if you take the numbers in the first row, our rate would be, all right, 3.5 times 10 to the minus 4. So I'm going to divide that by 0.2 squared. Right, is that what they've got in this one? It certainly is. 3.5 times 10 to the minus 4 divided by 0.2 squared. And yeah, you can check your calculator technique, see if it comes out at what they've got in the answer here. Yeah, good, good. 8.75 times 10 to the minus 3. Don't lose the 10 to the power whatever. And the units for that. Because it's a second order reaction, the easiest way to do it is go back to last week's notes or read it off here. We went through the whole performance of actually writing, working out the units. But for a second order one, you've been given them on here, so it's actually moles to the minus 1, decimeter cubed, seconds to the minus 1. The most ridiculous sort of contrived units, just to make sure that when you multiply that there by moles per decimeter cubed squared, right, you are then left with moles per decimeter cubed per second. So yeah, they're not units that you could actually describe, they aren't a thing, are they? If you were going to try and write that out, it would be decimeter cubed on the top and then moles and seconds on the bottom, wouldn't it? So it would be decimeter cubed per mole second, whatever one of those is. They become meaningless, don't they? So yeah, they are literally there, like I say, as a fiddle factor to get the units right. And yeah, I have a deep mistrust of chemical constants. Oh, it clearly isn't a constant, except for one reaction at one temperature. Okay, right, I think we better do a joint effort through the next one as well, haven't we? And then perhaps I'll let you loose on the others. Right, let's see what we've got. The hydrolysis of methyl propanoate, all right, you've got to think back to your organic for that, was studied in acidic conditions at 25 degrees C, and the rate equation was found to be, oh great, K times CH3, CH2, COO, CH3. All right, that's the methyl propanoate that we've got there. I would be very tempted to abbreviate that to something because its actual formula doesn't matter. And you'll find when we do the rate questions like this, there's a similar sort of question where they just call that X. Because it actually doesn't matter that it's methyl propanoate. But this is a reaction then. The two reactants are methyl propanoate. The first part of that, this part has got 3 carbons in it, and that's the propanoate. And then the CH3 is the methyl bit there at the end. Right, so CH3, CH2, COO would have come from propanoic acid. It would have just had an H on the end. That's been taken off, and the methyl group's been stuck on there instead. So methyl propanoate. So that's one of our reactants. The other one is the hydrogen ions of the acid. The rest of the acid doesn't matter. We have what we call spectator ions very often, and they are ones where there is no change in their electrons, basically. All right. Now, when we get onto the redox part of this unit, you'll see what I mean. But it would be what we'd call their oxidation number doesn't change. The charge on them doesn't change, that sort of thing. Whereas something will happen with this. I have no idea what it turns into, methyl propionate and hydrolysis, so it'll go back to probably methanol and propanoic acid then. That's, yeah, that would be the hydrolysis of that. Anyhow, do we care about that? No, we don't. All right, we're going to start off with the rate constant. How are we going to work that out? Well, we've got the equation up there, so you can use, you know, your approach is, right, well, let's just get this sorted out then. We've got, both of them are first order, aren't they? Or it's first order with respect to both of them. There are no numbers other than a presumed 1 there. So if we divide through by, okay, if we divide both sides by, right, I'm going to put just MP in there for methyl propanoate. And when you're working stuff out, you know, if it's not an actual answer, then, you know, it's okay for the time being. And we've got those numbers. We've just been given them in the table there. So this is not exactly a challenging one, is it? All right, as long as we've just rearranged that equation. You wouldn't have to know anything about rates of reaction to be able to do that. That's basic algebra. You then feed in your numbers out of this table. So the rate, 1.15 times 10 to the minus 4. And then we're going to divide that by these two multiplied together. So 0.15. Put the 0 in because it's to 3 decimal places for both of them is the correct way to do it, isn't it? Okay. Hopefully that comes out at, yeah, I appear to have done, oh, that's interesting. All right, we've got a range of answers here. 1.38 to 1.4, it does depend on your rounding. All right, so 1.38 would be accurate, so equals 1.38, and then they've given us a separate space for the units for this. And our overall, oh, well, what do you know? The overall order of reaction is 2, yeah, because the overall order, weren't asked for it, but the order is 1 plus 1. All right, we assume a 1 there and a 1 there, so the overall order is 2, and so it's the same units as last time. Well, it was moles to the minus 1 decimeter cubed per second, or so it should just say seconds to the minus 1, because per second then doesn't make any sense, does it? So that was a straightforward bit, honestly. Okay. Yes. To do. Okay, to divide the top. You need, if your calculator won't do it like that, the best thing is to put a lot of brackets in. Sometimes you have to force your calculator to do everything properly. You know, you might need to put brackets around that and brackets around that. It's putting that in sometimes is the tricky bit. You should probably be able to do the top bit without brackets, but just trying to think what it might do is if you then put divide, it might divide by the 0.15 and then multiply the whole lot by 0.555. You've got the risk of it doing oh, right. Perhaps it's likely to be the power of 10 that's causing the problem. And it's usually whether you have to put the number in before or after pressing the 10 to the x bit. But individual calculators, although it looks like you've got similar ones. But yeah, you have to sort of tinker with your calculator. When you know what the answer is, then at least you can work the sequence out. But yeah, I mean, these are not as complicated as some will meet, where we've got fractions on the top, fractions on the bottom, multiplying fractions together on the top, and multiplying fractions together on the bottom, and then dividing them. You have to get used to using memory sometimes as well on there.
If you get fractional orders.
Fractional orders are a bit weird, but we don't. We don't tolerate fractional orders. Not at this level of chemistry. I don't know whether any further than this you might do. But yeah, we would usually look to round them one way or another, so that it makes the maths a bit tricky. And yeah, what you do with the units, I have no idea. Yes, if your overall order was 2.5, I don't know what the units are. So yeah, no, we have to make them into whole ones. I think Jim Clark has something to say about it on the fractional units. But I can't remember. Sorry, fractional orders. But I can't remember what it is he says about it. But I think it's not. Basically, we don't do that. Right.
Yeah.
Now, if you want to start looking at the next bit, the reaction in part A was repeated at the same temperature, but water was added so that the volume of the reaction mixture was doubled. Calculate the initial rate of reaction under these conditions.
So you use the same.
The constant, yeah, the rate constant will be the same, because the temperature's the same. But what about the concentrations? Sorry? Well, the concentrations don't double, the concentrations half. Because if you've added the water, so you've got twice as much volume, then you've halved the concentration. So it would be, yeah, I think the important thing that they want from you here is remembering that, yeah, that the rate constant is a constant for a given reaction at a given temperature. And that's the trick, isn't it? So, right, in this case, what we're actually looking for, initial rate of reaction, so we can go back to our initial equation up there. So this time, rate equals, so very important that we're putting in our 1.38, but then we can halve the concentrations. So for the methyl propanoate, our concentration would be 0.075. Yeah? And for the other one, 0.222. No, 2.6. It'd be 2.66 occurring, wouldn't it? Yeah. So 2.67 then. 2 what? 2.775. I was out then. That's what happens when you try and do it in your head. 2.775. Well, we could keep that in, or because we've been working to 3 decimal places, we could. Yeah, we should probably. Don't know. Well, possibly round it. Yeah, could do. Right, what we got in here then? Do they give us that one? Right. Yes, if you have a look.
Isn't that 0.075?
You're absolutely right. Yes, it's 0.075, which was what my brain thought, but my hand did not write. 0.075. Right. Yeah, beware of decimal places. So are we working this right according to this? Yes. And we'll get anywhere between, well, to be honest, for the answer, sorry, for the rate constant we're using, which is the 1.38, should be coming out at 2.87 times 10 to the minus 5. hopefully. Are we agreeing with that? 0.02. Should have I read that wrong off the sheet then? It says to the -5. Oh, what? That's not 1.38. Right, yeah, I've looked at this wrong. I've missed a times 10 to the -3 out. Whoops. Yeah, okay. So that would work now then, wouldn't it? Yeah. Why did I miss that out? Well, I'm sure we said it as we were doing. So, yeah, so we should be. That sounds right now, because if you're saying point, yeah. All right, so that is 1.38 times 10 to the -3 times half of that, which was 0.075, times 0.2775. That should now be right. Yeah? Okay, sorry about that. But yeah, that's what I mean. You sometimes have to start at the answer and work backwards, and so do I. You know, it's that sort of debugging your calculations sometimes. And that's the benefit of writing out your working, isn't it? You know, if you're trying to learn something and it doesn't match, the answer doesn't match. If you haven't written out how you got there, you can't work out where you went wrong. But because, you know, I could compare with this, and having worked it all through and having written out that and realizing, you know, when I looked at this, the answer sheet, that we'd got something missing, you know, you can see where you've actually, you know, missed something out, or got something the wrong way up, or got a decimal point in the wrong place, and that sort of thing. Okay, right, I'm going to give you a little while to have a look at the other two without actually sort of just dictating it all to you, and you know, use the same sort of principles, and I will wander around and see how you're getting on with them. All right, looking at the next one. This one, I found this complicated myself because the table is the other way around from the ones that we've been looking at. So, first of all, we need to use the data in the table to deduce the order with respect to P. So let's start with P. If we want the order with respect to P, we keep Q constant. So that's here. It's those two. Reaction experiments 1 and 2, we keep Q constant, but we've changed P. All right? Now, you can do this either way round. You can either go, what happens from 1 to 2, in which case you half the concentration, or you can look at what happens between 2 and 1, you double it, because it wouldn't matter in the lab, would it, which way round you were doing it. You know, what order you do your experiments in is neither here nor there. So I will do it the other way round, the way that is actually the easy one to work out. So they're keeping constant, but this is times 2. When we double the concentration of P, what happens to the rate? 2 to the power what? 2. Now, if you were to do it the other way round, which is where I started, I'm going to mess this up by, I'll do it in another colour. But if you went the other way, that's times 0.5. Yeah? And from here to here, of course, is a quarter. So yeah, that's actually times 0.5 to the power 2. 0.5 squared is a quarter. All right, but that would be, and it's got to be, hasn't it, in the different directions. It doesn't matter what order you've done them in. So the order with respect to P, I don't know why I'm picking up it doesn't matter what colour pen I've got in my hand. Sorry, wrong one. So the order with respect to P is 2. Because keep Q constant, change the concentration of P, and then see what happens to the rate. So yes, either way with that. With respect to Q, I think it's a bit more straightforward, isn't it? I could do with another colour for that, couldn't I? Oh, that's green's the only other one I've got easily. If we're looking at the order with respect to Q, we've got to keep P constant. Well, that's constant between experiments 2 and 3 or 3 and 2, whichever works. It doesn't matter. All right, there's the constant. So if we're keeping that constant, when we double, so that's times 2, the concentration of Q, what happens to the rate? It goes up by 2. 2 to the power 1. Yes, that power is the important bit. That's the order. All right. And let's keep going with this and then move on to something else. Right, in a reaction between R and S, okay, something completely different. The order of reaction with respect to R is 1, the order of reaction with respect to S is 2, and the rate constant at temperature T1 has a value of, and I have a sneaking feeling, yeah, something's going to happen down there with temperature, yeah. Okay, and we've got a value at T1. A rate equation for the reaction. All right, let's go back to black pen. The rate equation, rate equals, what we told, the rate constant at temperature T1 has a value of 4.2, oh my goodness, times 10 to the 4, sorry, moles to the minus 2, decimeters 6, seconds to the minus 1. Okay. Right, well that goes with the overall order anyway. So rate equals K, which is 4.2 times 10 to the minus 4. And then all we've got to put in is R to the power, leave it, yeah, because it's 1. And then S, concentration of S to the power 2. So there's our rate equation. Now, calculation. What have we got to calculate? I'm sorry, I've lost. Yeah, I've got absolutely no idea what we calculate here.
It's the rate.
The rate constant at that.
Because you have the constant, you have the R, you have the S.
Do we have R and S?
Yes.
Where?
Just on top. You have.
Oh, I've rolled past that, have I?
No.
Oh.
It's just on the top. So it's R is 0.16 and S is.
Sorry, I literally just could not see that. Yeah, R is there and S is there, and I just sometimes it's when you stand so close to it, you know, that I'm having to step back. I'm looking up here and thinking, have I lost it? No, I have just lost it, I think. So the calculation, so our rate is, oh dear, 4.2 times 10 to the minus 4 times 0.16 times 0.84, I haven't left any space for an answer here, squared. And if that's a number that comes out the same as the answer on here, that would be great. So let's see if I've got that actually. 4.2 times 10 to the 4 times 1, yeah. So are we getting 4.7 times 10 to the minus 5? Right. That will do nicely. 4.7 times 10 to the minus 5. And because it's a rate, of course, the units that we'd want in there would be moles per decimeter cubed per second. They weren't part of the answer on this particular question, being an A-level question, but of course for me they would be critical. Okay, where do we go next then? The next one, second experiment at a different temperature. The initial rate is 8.1 times 10 to the minus 5, when the initial concentration of R is 0.76, and hang on a minute, and S is 0.98. Yeah, sorry, all the numbers were running together there. So it's calculate the rate constant. So that's just one way you rearrange back to say K equals, right? and it's your rate over, so where's our rate is 8.1 times 10 to the minus 5 divided by whatever we'd got on the other side. So the R was 0.76, and it's S squared, so it's 0.98 squared, I think. And there's a challenge for your calculators again. Have you cracked that now, James? Yeah?
Yeah, one of the
All right.
was the actual where you times 10 minus 4.
Fine. Oh, right.
Minus 4 is in C.
Oh, right, yeah. Yeah. No, you've actually got a button to press that'll let you do it, haven't you? Yeah. Yeah, it's good practice just in getting those right. Yeah, brackets all over the place solves a lot of problems. So, yeah, what we should be getting coming out of this, according to the answer sheet then, is, are we getting 1.1 times 10 to the minus 4? Okay. Okay, which of T1 and T2 is the higher? Well, I've lost T1. K for T1 was up here, which is bigger than that. So T1 is higher, because increasing the temperature increases the rate constant. Right. We've done more there than we need to do, you'll be delighted to know, because I'm not going to ask you to do these sort of calculations. It's just that getting used to the idea of concentrations, rate equations, rates themselves, rate constants, and all that sort of thing. So it's not something that, you know, is going to be part of your assessment or anything like that. So don't worry about it if you find it tricky. These were literally, as I said, just an opportunity to see some A-level questions of this particular type. Now, what I want to finish off with this afternoon is to get on to collision theory. So let's get rid of this. And I'm going to give you some printed off bits off Jim Clark's website, because it just saves me some writing. I am aware how much paper I give you with this, but yeah, I'll go through the key points in a minute. It's recycled paper. It's all right.
Trying to set up some of the power stuff.
Yeah.
Country, so I said just knock the forest down and build a new depot.
Oh dear. Not really. Right. We've met the factors that affect. Just as a quick recap, factors affecting rate. Right, this is literally just a recap. We had things like the obvious things that we were considering were things like concentration, temperature, and all that. But we will be sort of coming back to them a bit at a time. But it was very often it was related to collision theory. All right. We probably didn't call it that, but the number of particles you've got to collide, and the temperature, of course, will increase the rate of their movement. Yeah. So, e.g., concentration. I'm sorry, this doesn't make a lot of sense, but this is just me thinking on the board. All right, those both, concentration and temperature, affect collisions between particles. All right. Now, what is collision theory then? Well, this is the bit that you've got from Uncle Jim. Collision theory suddenly couldn't spell it. Collision theory itself. You've got to think back to the organic mechanisms as well a bit here, because you only get a reaction, well, you have to have two factors. You've got to have enough energy to break bonds, haven't you, in reactants. You know, think about the calculations using bond enthalpies, the breaking and making bonds, and the overall endo-exothermic thing. And, of course, they've got to be in the right orientation. And I think in that handout you've got, on the second side, yes, you've got some diagrams which sort of take us back to, that's your, oh, which one was it? The electrophilic addition, wasn't it? Where you've got a molecule approaching a double bond, a pi bond there, but it's got to approach that molecule the right way round, all right? And yeah, you've got to have the electrophilic bit, the electrophile approaching that bond to pull the electrons away, because if the other end approaches, it won't. And if it approaches from the side, it won't as well. So the sort of critical points here, you've got to have an orientation that will bring the reactant parts together in such a way that the sort of functional groups and things like that are orientated properly. I'm sorry, that wasn't really clear at all. But reacting, what should we call them? Molecules? Particles? Particles. Doesn't matter what the particles are. Must be in the correct orientation. Okay, you've got to have the right bits meeting the right bits. And secondly, they've got to collide with enough energy and this is where we meet the idea of activation energy. And you've got to have this minimum amount of energy to break the bonds. So enough energy to break bonds. You know, to start that process, and that's the activation energy. And we will be returning to that. All right, so those are our sort of requirements for a reaction. Now, in order to explain this, and the I think the last slide of this bit from Jim Clark has got this. It just takes you through these particular bits. It details a bit about the orientation with that example of the ethene and, I don't know, something like hydrogen bromide or whatever. It takes you through activation energy and draws the little graph that I actually drew in relation to the enzymes yesterday. But it then goes on to, and over onto the last page, the Maxwell-Boltzmann distribution. And this is the key bit. And this bit, you'll need to copy graphs like this into your assignment to explain some of the things that happen. But it's very straightforward. It's a really, really straightforward idea. The Maxwell-Boltzmann distribution. I don't need the board playing up as well. Oh, I have trouble spelling that. I've done it right this time. That's going to be the first time ever. TZ and a double N. Right, got it. Maxwell-Boltzmann distribution. If you take, it's almost like taking a population, if you like, but if you've got a system consisting of, this really has to be gases, to be honest, but we apply it to anything really. If you've got a container of gas of some sort, then the particles in that gas haven't all got the same amount of energy. It's a bit like us in here. Probably some of us have got more energy than others. I'm not entirely sure. Looking around the room, it doesn't look like many of us have got much at all. But you know, you could take a sample of people, and it's pretty much the same, isn't it? But the way that the distribution works, if you look over the page, you've got this curve that represents the distribution of energies. Sorry, that is a very badly drawn pair of axes there. And what we're plotting is the number of particles and the energy that they've got. And you can't have particles with an energy less than 0, and probably we wouldn't have any with 0, to be honest, but we usually start it down there, and most of them come into this sort of category. But then you get a tail off. All right, and so some of them have got very high amounts of energy, and some of them have got, you know, moderate amounts, and some have got very little energy. And the important thing about this is, you know, the number of particles that are involved. But we've just said that in order for a reaction to take place, the particles need to collide with a minimum amount of energy, and that's the activation energy. And if you look at the second of the graphs on the back there, the activation energy is defined as perhaps a point like that. Okay, so that's activation energy. And so quite clearly, not all the particles in this container have got enough energy to react. But any of the particles in this category here would have activation energy or more. So they would be able to react. Okay? And you've got labels that go with that. They're not terribly clear. They haven't copied very clearly. So this is, yeah, here we've got not enough energy to react. So if you added up all the particles in that bit, they wouldn't be reacting. But then, and my colours don't really work here, do they? The ones down at that end, only the number of particles represented by the area under this part of the curve have high enough energies to react. So high enough energies to react. Okay. Now, if you then sort of apply changes to your reaction environment or whatever, then it's going to have an influence on the number of particles with the right amount of energy. I mean, if you double the concentration, you will double the number of particles with enough energy, theoretically. It doesn't quite work like that necessarily. If you increase the temperature, of course, you actually will push the curve to the right. So more of them will have activation energy. So a lot of the things that we need to be able to explain in terms of the effects of changing conditions on the rate of reaction, we can illustrate with this Maxwell-Boltzmann distribution. Now, there is a comment on here right down at the bottom. You can change the shape of the curve by changing the temperature of the reaction. You can change the position of the activation energy by adding a catalyst. And that is, you know, that sort of meets nicely with the idea, you know, of enzymes as well. That we'll come back to this. I shall probably be back and forth over the same bits. But if you add a catalyst or an enzyme, then you can move your activation energy, say, to that point. And what that means is you've just got, I mean, I don't think I'd put it on this one because I'll do it separately, but if you add an enzyme or a catalyst and your activation energy is now at a lower energy, then immediately more of your particles have got the energy required to react. So the Maxwell-Boltzmann distribution is a useful way of illustrating why certain factors have an impact on the rates of reaction. All right, so we will need that as we sort of go ahead. Now, before we wind up for this afternoon, I'm just going to introduce the reaction that we're going to look at for tomorrow. And to put it on there, I suppose. This is one that's used very, very often in rate investigations. And it's a sort of baby version tomorrow of what you'll then do on a more self-controlled plan to, next week. You're going to, for the assignment, you're going to do the investigations individually, all right? And you will, you can do as many concentrations as you like, as many temperatures as you like. It can be a bit tricky sometimes to manage individually, but it's something that you have to get used to, I'm afraid. And this is the easiest one to do it with. I don't think you need 2 pairs of hands for this one. It's a reaction between sodium thiosulfate and hydrochloric acid. And I'm now trying to remember all the things that you actually get out of it. You get... I want the whole reaction. I can't find the whole reaction. We definitely get sulfur. All right, the sulfur is the important bit that we're actually going to spot. If you had to guess, what do you think we'd get as well? It's always a good option. I'm not sure you do with this one, actually. But if you've got to guess between those two things, yes, sodium chloride. Yeah. You also get I've got sulfate ions in here, but I thought it was yeah, hang on. I'm going to have to look it up because I haven't got it written down. And this is just one of those things which I assumed I'd got it on that sheet. I'd copied out the notes, but obviously not very well. Bear with me. It does not take long. Yeah. Okay. Okay, right, let's go through that again. Sulfur, we get the water, sulfur dioxide and sodium chloride. Oops, run out of space. What have I lost? Sodium chloride. Oh dear. Yeah, things get worse and worse with this. But yeah, you can see I started too far in. We don't need all of this. The important bit is really that we don't need the sodium chloride for a start. We need the hydrogen ions in here because they're having an effect. But the yeah, I want the bits that actually matter here. Sodium thiosulfate is Na2S2O3, I think. Hydrochloric acid is HCl. The sulfur, water, sulfur dioxide, and sodium chloride, they're relatively straightforward. All right, so we're going to lose some bits of this because we're not interested in all of it. The bit that we're really interested in is the thiosulfate ion. Okay, that's the first bit. We're interested in the hydrogen ions, although they aren't going to produce the product. They don't change actually in all of this. It's really only the thiosulfate that does. The second part of its name there. We can lose the sodium chloride. So what we're actually going to end up with is an abbreviated version of this. I'm not going to write it all out at this point and make mistakes that I've then got to put right tomorrow. All right, but the thiosulfate ions are the origin of all the sulfur that we get on the right hand side. So I don't know, does that actually balance as is? No, it doesn't, does it? Quite. We do, and 2 sodium chlorides will do the job, won't it? But we're yeah, that's what we're going to use, and it's the formation of the sulfur. All right, that is our determination of the initial rate. So when there's enough sulfur to obscure a spot or a cross on a piece of paper, then we say, you know, that's been the, you know, that's our stopping point. So we've got a time value for that. And what you're going to do tomorrow, I'll explain through it properly first, and I'll make sure I've got the equation right. You're going to look at changing the concentration and see how the time changes. And of course, if you change the concentration, you can measure the time it takes, and then you can do the estimate of rate by doing 1/over time. And more sketch graphs. You know, this is absolutely full of graphs. One thing I will say about the redox section is there's no graphs in that. All right, so yeah, once we're done with rates, actually equilibrium doesn't either. Once we're done with rates, you can wave goodbye to the graphs in this, I think. So yeah, if you change the concentration, we give you a standard solution of sodium thiosulfate, and you can dilute it by various factors. You know, you can do, I think they recommend using 50 centimetre cubed to start with, so you could do 50 of the original solution, and then 40 with 10 of water, 30 with 20 of water, and so on. You can do the same thing with the hydrochloric acid separately if you want to. So that's one part of the practical work tomorrow, and then we'll think about temperature, and I will properly introduce that Arrhenius equation, because that we can then use to work out activation energies which you can get from changing temperature. And then you can do another version of the same practical but changing the temperature. The way you change the temperature for this in the actual assignment practical is quite hit and miss, actually. I'm just thinking tomorrow, because we'll have had the water baths out. Oh, except I can't have you all round the water baths, can I really? Because we'll have the water baths out in the morning for doing the enzyme practical. It's actually, you know, this has got to be the only time this has ever happened that I've actually managed to get the theory and the practical of rates and enzymes even on the same day. So you should have a good understanding of it by the end of tomorrow. Either that or you'll be completely confused. But because we're not having to worry about an enzyme, we can just heat the thiosulfate up literally using a Bunsen. But you do find if you go above temperatures of about 50 or 60, it becomes less reliable, the effect on the results, possibly because it cools down very quickly as well. But yeah, you're going to look at the effect of temperature as well, and then hopefully you will be ready to start talking about the assignment. We shall see. Okay, we'll stop at that point then.